Thank you for joining us for this 25th SLiTHEr. Our speakers today are John Wisniewski and Tulay Ateshin. And they're gonna expand upon a NanoChat topic that we had, which is getting students started and continuing in research, and how they have kind of molded their approaches to this, hopefully to the student populations and their projects that they present to the students. So with that, I will hand it over to John and Tulay. I'm going to drop a review survey in the chat. So if you have a chance to fill that out afterwards, please do. All right, it's all yours.
Well, thank you, Matt. And thank you everyone for attending this afternoon.
Hey, everyone.
Tulay?
As Matt mentioned, my name is Tulay. I teach Gen Chem 1 lecture and labs from time to time in organic chemistry lecture and lab, advanced in organic chemistry, graduate in organic chemistry, and most lately graduate organometallic chemistry. And my research is more due to the COVID computational inorganic chemistry. We didn't go back to the lab. We chose to work off campus during the COVID, but I'm so excited to go back to the lab. John?
I'm John Wisniewski. I'm at Fairfield University. I'm starting my 15th year, I guess, next week. So I normally teach advanced inorganic, both lecture and lab in the fall. That's our only inorganic course. We're an undergraduate school for chemistry. I teach general chemistry 1 and 2, labs for those classes, chemical analysis every now and then for our sophomore majors. And I've developed an honors course for the honors program, Understanding Color Through Chemistry and Painting, which I've co-taught with an artist on campus, which was a lot of fun. We taught it for the first time last spring. In my research, I'm making lots of pincer ligands with sulfur, nitrogen, sulfur donor atoms, and first rail transition metals that contain these pincer ligands. And now we're making O&O pincer ligands as well. And we work with ourselves and collaborators to screen these for activity. Right now, a lot with electrocatalysis. Okay, so at Fairfield, we have about 4,200 students for undergrads. They have some graduate programs, but not in the natural sciences. Mostly those are in nursing, business, and graduate education. Okay, but not natural sciences. So I've worked at Fairfield, since I started in 2007 with students across all 4 years at the university. I've worked with 2 high school students as well, who were recommended to me by Fairfield faculty. So mostly I work with sophomore, junior, and senior students, but I work with a few first-year students along the way. A huge majority were chemistry and biochemistry majors. I worked with a finance major who I had in general chem. 1 and 2, she should have been a chemistry major, but she chose finance. As I said, a good number of the students took general chemistry 1 and 2 with me. At Fairfield, advanced inorganic is a senior course. So if I waited until I had them as seniors, I would have a group with a lot of turnover, and by the time they get some skills, they'll be graduating. So I try to start them early. At Fairfield during the academic year, students must register for academic credit. So at Fairfield, it's a 4-digit 497X, where X is the number of semesters in which you've done research. So the first semester is 4971, second semester is 4972, etc. If you have an ACS certified degree, and not all of our students choose this pathway, you need to have at least 3 credits for an ACS certified degree. And the number of credits depends upon how many hours a week you're spending in the lab. So for 1 credit, it's about 3 hours per week. 2 credits is 6, 3 credits, it's 9. And all the students, no matter how many credits they're working toward, we have a Friday afternoon seminar, Fridays at 2, where either students present or We bring in outside speakers, or we have some sort of activity for them to do. And students can work in the lab, in my lab, when we're both free. So if I'm teaching another class, they can't work in the lab. If I have curriculum committee meetings on Tuesday afternoons at 3:30, they can't work in the lab.
So to follow up what John just talked about, I want to talk to you a little bit about UTRGV, how we compare to Fairfield. We do have a master's in chemistry program in addition to our undergraduate. So I mostly work with the juniors, seniors, and graduate students, not by choice, since I have been teaching mostly inorganic chemistry, which is a 3,000 level course. I have not been able to recruit students in the freshman level from my Gen Chem lectures. If I teach Gen Chem lab or lecture, then I also like to get them started early in the freshman year. So our main concern is the late start dates for research. So the sooner they start is obviously the better, but I don't meet them up until they're juniors and sometimes seniors. So for our students, I have students from chemistry and also biology majors, particularly the pre-med students, and they wanted to do more medical related research in chemistry. I also mentor graduate students in the master's in chemistry program. So the students, I usually meet them in my inorganic lecture or laboratory classes or advanced inorganic lecture. But when I meet with them in the advanced inorganic lecture, that will be really too late to start any type of research unless they consider attending the graduate school and kind of get started in research as an undergraduate and continue in the graduate school. So our chemistry problems course is 2 credit hours. So this is required for ACS certified degree. And that's part of the problem where we have students wanted to do research with us in their senior year without any prior research experience. And it's very difficult sometimes to welcome them in their last semester. And I had a student actually who delayed his graduation, and Chem Problems was the only course he was taking just because he started that late. And for the undergraduate students, I try to meet with them at least once a week because they need more help than the graduate students. So we have once a week research meetings. But for undergrad, it's mostly teaching. I sit down with them and then teach them research methods if they don't really have an idea what they should be doing and how they should be doing it. And due to that time commitment, I try not to take too much of undergraduate students, and I try to focus on more graduate students and maybe graduate students mentoring undergraduate students if I don't have the time. I don't think I can advance the slides. I'm trying, but it doesn't work for me. Sorry about that.
I got that. Okay. So when I work with students, in my lab, I try to introduce them to the community. Oftentimes these are, first year students. I started with 2 first-year students last spring, March and April. And we give them some articles. Sometimes they might be articles which I wrote, just so they get some background in the area. I start, we can set up a SciFinder Scholar account for them because we have that at Fairfield U. And they can start learning how to search for things, okay? I understand they don't understand everything in the article, but they might get some points out of it and they can ask good questions. And so they can learn more from that way, okay? I always pair my beginning students with more senior students, and I always have them start off by preparing starting materials in the lab. Okay, so these are things I know work. We've made many times, but they get some skills in doing so. They build some confidence along the way. It's new for them, so they're excited about it. The experiment works, so they're not that frustrated. So just by doing so, they get to learn how to set up reactions, purify products, running TLCs, running columns sometimes, characterizing products, a lot with NMR especially. We do some UV vis as well. Mass spec as well. The students have to maintain a detailed lab notebook. And I give them model notebooks from previous students so they can follow that. So for instance, I want, everything, mass and moles of everything, where the reagents came from. If the NMR was created, what day, because the way the file keeping, it goes under my file, and then what day it was. So this way they can, keep a good notebook so I can look at it afterwards after they graduate if I need to. So then, once they make the ligand precursors, they have to work with more senior students to metallate. Okay, and we do focus a lot on first row transition metals in my lab, primarily because they're more less expensive, and they learn how to grow single crystals and some of the techniques we use to grow single crystals in the lab. Okay, so they learn a lot. They love it when they make the metal compounds because they have all the neat colors of the metals. And they really learn their way around the lab, right? So oftentimes they might start with just for 1 credit or 3 hours per week. And they learn a lot in that process. And then as they become more mature during their junior and senior years, they might do 2 or 3 credits.
So this is a sample notebook page, which I added right after John's slide, since I mentioned about notebooks, but I'm also gonna talk about it a little bit. Okay.
So, oftentimes when the students come to Fairfield, the senior students mentor the newcomers. I'm always in the lab with them as well. I moved into a new lab 2 years ago, so I've got a lot of a good spot to hang out and help them. Even though they're doing a lot of the chemistry themselves and they're doing the work with their hands, I'm there to help and teach. It's really good to have other students mentor as well because they learn from them as well. And as I mentioned before, the students present their research to other students and faculty in our Friday afternoon seminar series. And I always mentor all the students, no matter what level they are, as they prepare for their presentation. And they know the types of questions some of my colleagues like to ask. So we make sure we have answers for those questions in their presentations, so it goes much smoother.
So UTRGV, as I mentioned, our main concern is them starting really, very late. And so instead of the work, I should have just revised the junior level in organic chemistry laboratories to introduce research methods. So I designed this course so that they can actually, if they haven't started doing research, they will be ready to chem problems course with not only in the field of inorganic chemistry, but in general in organic chemistry, and pChem, and biochemistry after taking inorganic chemistry laboratory course. So the first meeting, we introduced the SciFinder Scholar. So this is not in the lab, but it's a computer lab. And we set up their accounts and we teach them how to use the SciFinder Scholar. I will show the course schedule a little bit in greater detail in the next couple of slides. So we do have librarians who can help students with SciFinder Scholar searches, but we don't have a chemistry librarian. So in the SciFinder Scholar training session, we focus on the structure editor. So we guide them to draw the chemical structures and then look for the papers. And at the end of that lab session, they actually save their search and they email us the PDF of their search for credit. And then we talk about how to set up a reaction, and most importantly, picking out the procedure that we find a couple, and then we divide them into groups and they all present different procedures, and then we make a decision collectively which procedure to follow and how to set up a reaction. And then we talk about the purification and characterization of the products. We mainly use NMR spectroscopy, or that's the technique that I've focused on to have them experience using NMR spectrum. And then we do have a very detailed laboratory notebook, and they also learn how to write a laboratory report. But this report is quite different than their previous laboratory reports. This is one report for the whole semester, and it's mostly in the paper format. And then I choose that, again, preparing them for the chem problems. I give them the chem problems final report guidelines to prepare them. So this is a trial for them to really get ready for independent research. So the most important thing is, of course, to do this in a classroom, in a group environment, to have confidence and also get ready for being independent in the lab. If they join my group without taking the inorganic chemistry labs, I have not been teaching this lab for a couple of years now, then I pair the students with the graduate students, so they actually start working on a volunteer basis. I really cannot accept any students because of the time commitments. Prior having some kind of a voluntary internship so that they know these techniques if they haven't learned in the laboratory, so that then I sign the form that allows them to register for the CAM problems. So the textbook that we use for inorganic chemistry is the primary literature. We don't really have a textbook, or we don't have the set experiments, although we do have those experiments and undergraduate students tested them. They really don't know that they actually had that experience or expertise. So the main course objectives is, of course, to develop their synthetic skills of ligands and inorganic compounds, to learn how to use NMR, interpret the data, and draw appropriate conclusions. So whenever we have our data, every group's data is slightly different. So we made copies for the whole class, so they actually compare and share experiences. And then finally, the writing skills. So I share with them several articles in the undergraduate level, how should they start writing and thinking about writing. So they first write from their results, and then going backwards, they write their introduction and abstract at the very, very end. So the learning objective, the main learning objective for this course is really interpretation of the data, getting the basic laboratory research skills, and also gain oral and written communication skills. So in regards to the grading policy, so this is actually one single experiment or one single project divided into 3 different experiments. The first experiment is synthesizing a ligand. The second one is synthesize the middle complex. And the third one is testing its catalytic activity. And the literature search is the first fundamental step. And then although we do the first time around in the lab together, and there are a couple of SciFinder searches throughout the semester that they should really, every time that they have an issue, they have to go back to the literature and try to troubleshoot. Then the second one is a literature presentation to just understand what other options are out there regarding the synthetic procedures. So we talk about the safety, laboratory safety. We talk about the practicability of some of the experiments, the low temperature experiments versus room temperature experiments, the reaction times and such. We talk about the reagents, the safety of the reagents. We try to avoid using lithium reagents at all costs, if it's possible. If not, of course, we'll teach them how to use it, but if there's a work around it, we talk about why it's important for us to think about safety always when we choose a laboratory procedure and practicability. And then we put a lot of emphasis, of course, laboratory code of conduct. So I'm just going to go back again really very quick. Okay, so, oops. Sorry about that. And we do have a very tentative schedule, but that actually fluctuates quite a bit depending on how they're proceeding. And the online quizzes are very simple NMR quizzes or chromatography quizzes, just to make sure that they do their assigned readings. So this is just a tentative full schedule. Again, we meet the first time in the computer lab, and so some of them are not in the lab because our labs were not equipped to do any PowerPoint presentations in the past. So we actually do them in a conference room in the computer lab if necessary. The second meeting is discussion of the notebook and then literature presentations. And then we start with getting ready to set up a reaction, of course, drying glassware and talking about air-free reactions is really kind of important. And then we introduce the TLC. They actually learn how to do TLC, although, I wanted to assume that they learned all of this in the organic chemistry lab, but they don't really have much experience with column chromatography or even NMR. So it's very surprising to me sometimes that it's the first time that they actually learn about the NMR technique. And then we focus on the phosphorus NMR and then conduct our first experiments. So up until mid-semester, we're still introducing the methods, and we start our experiments quite late in the semester. And then sometimes do only 2 experiments and not go to the 3rd experiment because of the troubleshooting that we had to do along the way. And then let me proceed to the next slide. Oopsies. All right, so I think talked about that. So this is a sample presentation, what we expect from students to do. And this is, again, most of the time, this is the first presentation that they're giving in literature presentation that they're giving in chemistry. So we focus on, for example, importance of citations. So they don't really get this right most of the time, and they just write the release date, and we just talk about the ACS and other citation formats is a starter. And then we talk about the naming. We go over the naming and then writing the reaction, balancing the reactions and such. And then in general, when we talk about the techniques, this is the first time they hear about the Schlenk techniques or air-free nitrogen atmosphere. And then the distillation, how important it is for us as an inorganic chemist. And then we talked about the procedure. So one thing that I really want them to look into in the procedure, some of them are really very vague, and they don't specify the time or the volume. The specifics of the experiment is really not there. And if they can't reproduce it, then I will just advise them not to use that procedure. Then the most important part of this literature survey is for them to be able to see pros and cons. And so the pros is, of course, they were just saying that this is very detailed, so it can be doable. And then they also mention if there are things that they don't understand, like, for example, crystallization, they have no idea how to do it. It's like, how long do I have to wait for crystallization? So we talk about some of the questions that they might have. So this is our first experiment that we actually, again, picked ahead of time, but we kind of guide them slowly and surely by the process of elimination of the other procedures to this particular publication. And in the experimental, we again talk about the Schlenk techniques, dried and deoxygenate solvents. So we actually bubble our reactions with argon gas. So we don't do freeze pump thaw in a teaching lab with so many students. And we start also talking about NMR spectroscopy. Then in terms of the procedure, so this is the one that had quite a bit of details and it's very doable. And then they set this up. So we actually teach them how to remove the solvent, rotovap. And then teach them recrystallization or precipitation, and then we dive into the phosphorus NMR. We only expect to see only one peak, but we don't get only one peak. Again, that's because it's the first time that they're doing air-free synthesis, so air gets in. And that's also by design, by purpose, that we rarely have one single peak. Then we talk about what could go wrong, like what just happened. And so then we discuss, so we go back to the literature and look at, we oxidized our phosphine. And we just talk about in this literature article that when it's oxidized, then it's no longer a single peak that we were expecting to see. There will be multiple different oxidation products as a result of oxygen getting in. So that's the point where I said we have a tentative schedule, but now we have to go back again to do the first experiment because we don't have a ligand to make the metal ligand complex. So that kind of takes time, of course. And then these are the instructional documents that we use. I gathered them from various different resources, but mostly PhD institutions where they have a very nice way of NMR sample preparation guidelines, and I didn't develop them, but I think it's important for me to direct them to these resources out there. If you get stuck, go to to research it. You will find very good tutorials and step-by-step guidelines for everything that we actually wanted to accomplish. Oh, I don't know what just happened. We have 2 more slides. Apologize for that. I can entertain any questions if you have any.
All right. So, when students, at Fairfield, they have the opportunity to work multiple semesters, and a lot of students work, for 2 or 3 years with a certain faculty member. There's money available for students to apply for research grants in the summer from the Office of the Provost. They have to apply for this money, so normally they apply in like February, the summer before, and they need letters of support from the faculty member with whom they're going to work. From the same pot of money from the Provost's office, there's also a lot of money available for them to travel. They love to go to ACS meetings to present their work. They just have to apply in advance. They've been very successful in getting money, especially if we take groups of students. This way the students can room together. Students, work multiple semesters, and most do can this project through, right? So they can see, the first semester they accomplished A and B, second semester C and D, hopefully, and then each semester, each summer, they made more progress in the project. So they like that. And a lot of my students are part of the university honors program. And as part of this honors program, they have to write a thesis or a really detailed report based upon original research, right? So in the natural sciences, it's easy, right? 'Cause that's based upon lab work. And in other areas, that might be something different. But this is a good way to really keep really good students, because they know they have to write their thesis, and they can write their thesis based upon 2 years of work if they want. So they can really combine everything and write a really detailed report. So when you're writing a publication, you have all that experimental data there and a lot of literature search stuff there as well.
So UTRGV, the first thing that I will ask students, of course, complete their camp problems requirements. And if they want to continue with, again, research, then they can take camp problems for the second semester as well. So this is elective, upper level elective, but it's not really required. And for the honors students, not only they have to write a thesis, and it's a 3-credit course, but they also have honors defense. So it's a 15-minute presentation that they have to do with the committee members and the dean of honors program. We also have Engaged Scholar Award. I would actually use this award after camp problems too, if they want to continue research for the 3rd semester. So I have a student who started last fall, and she did research with me in the fall and the spring and the summer. And I encourage her to apply because she will be graduating in the fall. And I think it will be great for her to get acknowledged for her persistency. I don't expect them to stay that long, that committed, particularly if they're graduating, but she is really outstanding. We also have Student Government Association travel support. So if they go to the ACS meetings, or we have Texter in Austin, that if they want to go to more local state of Texas conferences, that they can travel to those as well. And yeah, other than this, I think for me, continuing students in research is probably not as a bigger issue than getting them started. I'm really struggling with meeting them early on in their careers, just because I don't teach lower level classes than 3,000, but that's my biggest challenge, or that's most of our challenges, particularly the PCAM faculty too. They don't meet them before their senior year, and it really hurts. quite a bit our recruitment efforts. Thank you.
Thank you.
Mhm.
Sorry, I was muted. I wanted to thank John and Tulai for their presentation, and open the discussion up to if there are any questions. So Tulai pointed out that her hardest thing about getting students started is recruitment. I'm lucky enough that I teach general chemistry, and that is a nice gateway into recruitment. What do you find the biggest obstacle, I guess, for continuing those students in research? So our students don't necessarily have to sign up for a course or anything like that, but for me, getting a student to stick around for more than a semester or 2 semesters has been very difficult. So there's a huge amount of turnover. And so I was wondering if both of you have a specific strategy you use, something you hang over their heads or something like that.
Well, I don't hang anything over their head, but a lot of my students have aspirations for medical.
Uh-oh. John froze.
Maybe publication. Hi, back.
Yeah, you froze on us, John.
Okay. Oh, okay. So a lot of my students have aspirations for medical school or PA school or graduate school, so they know that there's a good chance they'll get publications out or presentations, and that will help them gain admittance to where they want to go after Fairfield.
Yeah, I use a similar approach too. So Chem Problems is, for example, is the one that we're lucky to have, although it's heartbreaking that it delays some of the students' graduations just because nobody have told them when they're sophomores or juniors, they come to senior year, and then the first time they hear about Chem Problems, like, what is that? Like, what do I do? Where do I go? And how do I sign up for it? You know, it's really heartbreaking. We don't, unfortunately, advise our students. The advising center does that, and there's a disconnect. And it seems like guiding the students early on what they need to do to graduate in a timely manner. But for continuation, I really use these mechanisms in the university that if they invest the time, that they should get credit for it. So course credit is great. If not possible, then the award, Engaged Scholar Award is great. And each one of them have a very, it's very structured. They have to write a report and they have to present a paper. I mean, they have to have oral presentation. They also have to write a formal report. And that really helps me. And also it's a set standard for the department that they have to follow the guidelines of the course. So it really helps quite a bit that it's not me imposing anything on them, but I'm there to help them to graduate along the way and guide them with the degree requirements. So I think that really helps me quite a bit.
Thank you. Adam or Ashley?
We do something. Well, there was one comment and then another longer thing. We actually do PChem first at Harvey Mudd. And so our students see the PChemists early, and we pushed organic then to the spring of the sophomore year. So the synthetic chemists at Harvey Mudd are the ones who are pushed later in terms of student interest in recruiting. But that's actually going to be changing. And we're going to move organic into a more normal time slot. One thing we do, though, that we started, 10 years ago, is we have a course in the spring of the first year, which is called Introduction to Research. And it's limited, we offer it to basically the number of students that we can handle. So we, poll the faculty every year, and I can take 2, I can take 1. And often they are either shadowing a researcher in your lab, or they come in teams of 2 or 3, and they do a series of rotations, so like 3 to 4 week rotations. And we found, I don't know that we've had really good success in terms of recruiting students to the major, but we certainly have had success in getting students doing research early. One of the students who actually just graduated last year as a computer scientist, she spent the spring of her freshman year working in my lab. That turned into a summer job the summer after her first year, and she got her name on a paper in a chemistry journal, but she's a computer scientist now. And so it's just interesting how that sort of works out.
It's really cool.
My problem, or what will become my problem when I finally get research started here, is kind of unique, I think. I work at Springfield College, and we do not have a chemistry major at all. I mostly teach, my responsibility is general chemistry largely, though I do teach an analytical or a PChem with biological applications, in the spring. They kind of go back and forth, but we have bio majors and we have a lot of health science majors. And, there are people with pre-med interest, so I think that's going to help. And I'm a computational chemist, and I've worked with students as early as their first semester of college. So I don't worry as much about getting them into the research, but how do I convince them that it interests them,
Well, I do have a similar challenge in my inorganic lectures. And most of them are biology majors and taking it for their chemistry minor. And sometimes I struggled making the connection with sodium potassium pumps or some of the biological systems, like why this is important. And they really use it to get ready. So for inorganic, like the concepts that we teach, they're very fundamental. Even in PChem, it's bonding and structural bonding, really very core to what they will be doing. So I actually remind them, if they're going to take MCAT or DCAT for the dental school, that they really need to understand the structure and bonding. So I try to not show them this as, chemistry majors, or it's equally important for biology. And I also had students who are interested in machine learning from engineering or material science. At some point, we're working on lithium batteries, making literally batteries and testing them. So it's possible to recruit students from different backgrounds as long as it's structure and bonding, and try to help them understand how the chemical structures are so fundamental in science and engineering. That's what I try to do. I try to state very basic, so that we always go back to the basic fluid structures, the bonding, which we teach the first semester of general chemistry, right? So my research, regardless how advanced and how crazy it gets sometimes, we always go back to the fundamentals.
Yeah, thank you. I think some of my background from my PhD was in like small peptide chains. And I think that'll help too, because a lot of our students, especially those interested in the medical field, do biochemistry. So even just seeing the peptide bonding over and over again and getting familiar with the R groups, defining which amino acid it is, those things are definitely useful. Yeah.
Yeah, definitely. It's intimidating. Like for me, it's very intimidating to have, biology seniors as the audience, because that's the first question that I ask. I walk in, who is my audience? Do I have any chemistry majors? And sometimes I don't have. There were sections that I don't have any chemistry majors. And then sometimes it's difficult to have them invested in, because they say it's a degree requirement for chemistry minors. So, but I'm like, but you're still. And one of the tricks that I used in the past is, I didn't mean to really, like, I didn't plan on it, but I invited my previous students to just come and say hi. And one of them just walked in from medical school and said, this course I took helped me a really great deal in MCAT. Pay attention. And it's really important. So don't just think that it's an inorganic chemistry, but it's really part of, your career. So that really helps, having the students have just come and talk to your class and just showing up and saying, it really helped me, that they really don't maybe associate themselves with chemistry because of that it's not their major, but still helps them quite a bit in every branch, including all branches of sciences, but also in engineering. It really helps them.
at least some of my research, I can really bring in more biological applications, since my original goal was to make some model compounds for liver alcohol dehydrogenase, so they can see that relationship to, bio-inspired chemistry, which, a lot of our students at Fairfield are maybe 2/3 or so are biochem majors, so they see that connection right away. So that helps as well.
Yeah.
I've been very lucky. Most of my students are biology majors that I've had over the years, and that's because our biology department is mainly wildlife. So anybody interested in molecular biology, even though it's chemistry, they find research that kind of gives them that lab skills in that case. So that's been helpful for me. I don't know if Ashley, that might be a selling point is with biology or
yeah, I think it really is. We have 2 biology majors here. So we have sort of a traditional like plants and ecology based biology. But our big thing here at Springfield College is athletics and physical education and physical health. So we have what we call a sports bio major, which is more human focused. And that does focus a lot more on, the cellular molecular level. So I think that's a big selling point.
Absolutely. And the other thing that I focus on when I talk to my students is that all the barriers that we built in academia, where it doesn't really exist in real life, and we boxed everything, and now we're trying to break those barriers, break those walls. And I try to introduce those concepts very early on and say, don't really think that chemistry is different or functions outside biology or sciences are so different than engineering. And we really need to build these collaborations and interdisciplinary teams, and the new generation of scientists should be able to speak multiple languages. Because I talk to them that whenever we want to have a collaborative project, even with my organic colleague, he calls it a ligand, I call it a ligand, and we call it the same, tomato. We have a language barrier between us, between chemists. So I try to emphasize that, it's totally okay being in engineering or in sciences, different fields of sciences. We really need to break these barriers and be more interdisciplinary to tackle some of the problems that we're facing as humanity. But unfortunately, it's a great challenge as someone who doesn't know enough biology or biochemistry for me to communicate with them, but they actually can make that connection and explain it to their peers a lot better than I can explain something outside my field. So that really helps to just encourage them to learn something outside their field as well. So it's kind of like being bilingual, trilingual when it comes to marketability. Like everybody knows biology, because if you're a biology major, you should know that. But having 2 minors, 3 minors, I had a student with 3 minors. I had no idea how she did that. But that's really important for them to get into these very competitive programs to show unique set of skills that is not really very standard. Like what makes you to stand out as a scientist or as an engineer. So I use that approach to recruit very unique set of students with very different skill sets. So it really helps them. Everything we do is for them. So I think the more we think about how it's going to help them, then it's very easy to get them invested in their future. If they have any questions on how it's going to help me, then maybe it's going to be difficult. But if we can frame it that this is going to put you in a unique situation where you will have this cutting edge or this edge compared to other applicants, then it really helps them.
I was wondering if, and this question goes out to everybody, if there's a particular way you approach projects with students. So when I started out, I had, hey, this is what my research is. And now I am all over the board investigating different things and playing around with what students are more interested in or where their strengths may lie. And I was wondering how everybody else approaches research, especially with the freshman student or, you know, the graduating senior, whichever it may be.
What do you mean by approach?
Like, so how do you, I mean, do you have it just as, this is what my research is, it's very linear, and a student, you know, you just pick it up as a student goes on, or do you have multiple projects that you kind of pick up and drop here and there, or even start something new based on what a student may be interested in? I guess that's what I was getting at.
I think early in my career, I had probably 2, maybe 3 sort of main projects, and I would put a student on the one that they liked, and that collapsed due to down to 1 project because I was getting results there. And so for probably 10 or 15 years, students who joined my lab did catalytic asymmetric hydroremination, right? That's what they did. And then with the ending of that project last year, this is going to go live on YouTube, right? And my students aren't going to watch this. So for what I tell other faculty members is the students are just going to be mixing stuff together to make cool compounds, and I'm going to get crystal structures of them. What I'm going to tell the students, though, is of course we're doing electrocatalytic CO2 reduction and hydrogen bond networks with chiral scaffolds, right? But that's really not what we're going to be doing. And I'm building this project, and I'm going to see what happens. But the students like making stuff, right? They don't care what they make, really. I mean, the synthetic chemists do. So they, you know, mix some stuff together and get crystal structures would probably be a better, more lucrative selling tool. But it's hard to write a thesis as, you know, mixed crap together in Prof. Johnson's lab. So I'm trying to make it a little bit more academic.
Well, I tried a couple of different approaches. So I tried a little bit of everything, including, as I mentioned, like breaking the boundaries, like I really tried to communicate or collaborate with the engineers on lithium ion batteries, or with medical school on cancer diagnostics. But I really didn't see myself contributing too much because I couldn't develop these expertise in multiple different areas. Then my most current focus is, you know, organometallics and computational organometallic chemistry, which is super interdisciplinary, or actually subdisciplinary by itself, that it's organic, inorganic, it's computational. You know, there's still quite a bit of learning opportunities. And I try to stay focused. So that was really what was missing in my earlier years, that I was all over the place in medicinal chemistry and engineering. And I really love that diversity, but it's very difficult to be able to keep that momentum for years to come, and also grow in all these different fields. I had prior experience from my postdocs that I did medicinal chemistry, postdoc at Northwestern material science, postdoc at Northwestern again in computational medicine. But it's very difficult to actually, because I didn't do them all simultaneously. And here I was a fresh assistant professor giving a keynote in medicinal chemistry there and submitting another grant in materials. And I was really all over the place. So right now, it's mostly what I tell my students when they come in. I give them the most current papers from our group in the last 2-3 years, and I tell them, this is what we're working on. When you read this, are you being inspired? Do you really want to jump into this work? Or do you feel like this is not for me and not being excited that there are no fireworks? So that's what I try to do right now, that instead of we still explore machine learning. That seems to be a service to the students in the long run, but I'm still not feeling that it's the right time for me to start machine learning. Perhaps after being promoted to full, maybe in the next 10-15 years, I might just invest more time to it. But I don't really see myself, and also see myself as an effective mentor for my students and growing professionally if I dive into so many different areas just because I felt like the kid in the candy shop. I want to do this, I want to do that, but there's not enough time and I couldn't read the literature. I fell behind reading the literature and also providing them advice and guidance just because I just couldn't keep up. But yeah, I tried both approaches, but right now I find it more sustainable when I tell them this is what I know and this is what the group does. If you're interested, welcome on board. If not, I encourage you to go and look at other faculties' publications and see what your passion is.
See, Adam wrote something in the chat, but I just wanted to, before I talk about that, I just want to go back to Matt's question. So oftentimes, I might have multiple aspects or different, different parts of a project. So I might have students or groups of students working on different aspects, and hopefully that comes together to make the whole project. So for that, I mean, some students might be working more imidazole type ligands, others might be working more triazole type ligands, for instance. I had one student, she's a high school chemistry teacher now. She just got accepted a job as a high school chemistry teacher, right? So she was more interested in chemical education stuff. So we did some work in the lab trying to come up with a chemistry, understanding more about a chemistry demo, which I did in my advanced inorganic class. So we made some more other ethylene diamine type ligands, metal complexes, and grew single crystals of those, and got crystal structure. So we published that. So with that project, it really didn't pan out the way we originally thought it would, but it worked out. So she got rewarded with publications at the end. So that helped. That helped her. So Adam wrote in the chat, "What is the literature?"
I'll say also, my research has been pretty air sensitive. I've been doing early metal compounds, and I've spoken a lot with Kyle Grice over the years, who's at DePaul, and an alum of mine. Actually, I have this inorganic lab chemicals here. I keep meaning to send these to you, Kyle. But he told me, why do you do air sensitive chemistry with undergrads? You should stop it. And so that's one of the things I'm trying to move towards is just do some bench stable chemistry, because it's hard enough, especially with first year students. But I did a lot of ligand design, so that my earlier students tended to make ligands and my older students tended to make complexes and do catalysis. Managing it is just impossible. And actually what I'm doing this year is, in terms of the literature, I'm having my students do the literature reading for me, right? I don't have time to read the literature. I haven't read a paper in decades, right? But my students can, and I can read what they write, and it keeps me abreast of what's going on. So I think that's a nice way to, it's research for them. And if it helps me, that makes it better.
A win-win for everybody that way.
Yeah, that's true.
Yeah.
That's true.
Well, it looks like we're just about out of time. I dropped the review form back in just in case you needed the link again. I want to thank John and Tulay very much for the discussion, and also Adam and Ashley for contributing. This has been a nice way to see how people get students started in research and how we continue. And hopefully this will be a nice resource for newly starting faculty in particular. I don't know if there are any closing comments or questions before we end. If so, no? Okay. Well, I thank you all very much. Thanks again. Bye.
Thank you, everyone. Thank you. Have a good afternoon.